Now, there are different types of magnetic materials, and there are essentially three ways that materials can respond to magnetic fields. The first two involve the response of magnetic dipoles to an applied field that returns to its starting point when the field is removed. These are weaker types of magnetism, and you don't generally see them. The last one, ferromagnetism, involves a remnant alignment of dipoles even when the field is removed, and this makes permanent magnets. Now, briefly to look at diamagnetism and paramagnetism, as well as ferromagnetism. Now, many common materials such as water, wood, plants, animals, diamonds, etc., are usually considered to be non-magnetic, but in fact, they're very weakly diamagnetic. So diamagnetism is caused by paired electrons in atoms. Diamagnetic materials are repelled by a strong magnetic field. The electrons in the diamagnetic material rearrange their orbits slightly, creating small persistent currents which oppose the external magnetic field. One visible effect of this is diamagnetic levitation. One great example you can see on YouTube you will find just by entering the search term levitating frog. Take a moment to be impressed by Andre Geim, who levitated the frog and was awarded an Ig Nobel Prize for it in the year 2000, but then went on to win a Nobel Prize in 2010 for his work on graphene. He is the only person on record to win both of those prizes. He has been quoted as saying, "Frankly, I value both my Ig Nobel Prize and Nobel Prize at the same level, but I don't think anyone believes him." Now, ferromagnetism. These materials contain unpaired electrons. So they do not necessarily act as magnets all the time, because the unpaired electrons can be oriented randomly, whereas they would all have to be lined up for their magnetic fields to actually add up to an overall magnetic field. Some igneous ferromagnetic rocks are permanently magnetic because they formed in Earth's magnetic field, and just as the crystals formed, magnetic domains formed, where the magnetic moments of the individual atoms lined up with each other in a small region called a domain. Normally, the different domains are randomly oriented, but if you apply an external magnetic field, all the domains line up and the material becomes magnetized. In hard iron, the domains will not shift back to their starting points if the field is taken away. But in soft iron, which is not literally soft, just different magnetically, the domains return to being randomly aligned when the field is removed. So you can think for yourself, what kind of iron would you then need in the core of an electromagnet? Now finally, paramagnetism. It's similar to ferromagnetism because the material is attracted to a magnet, not repelled, and it is found in any material with unpaired electrons, not just ferromagnetic metals. But it's a lot weaker than ferromagnetism. And because it is easily destroyed by random thermal motion, even at room temperature, you generally need to cool a material to very low temperatures before you see it. The picture here shows liquid oxygen caught between the poles of a magnet. Paramagnetism is also different from ferromagnetism in that it disappears as soon as the external field is turned off.